So this is kind of a cartoon drawing of blocky veins. They're clearly not all equal size, but none of them look long and fibrous, and there's not a massive difference in size. On the other hand, here's a cartoon drawing of a fibrous vein. You can see it's not the actual black lines, but it's the white space between them. Each long, thin white area is one fibrous mineral crystal. Here's an example of fibrous mineral forming in a vein. This is a chunk that's been taken out. So, what can we interpret from a fibrous vein? What can it tell us, other than, hey, that looks cool? Well, there are two ways. You can have a syntaxial vein, where the vein fill is the same as the wall rock. So basically this is, okay, we've got our joint, we've got water flow. That water is dissolving the wall a little bit and redepositing it. So it's just kind of a recrystallization, but an aqueous recrystallization of the material that's there. And then antitaxial veins is when the vein is different than the wall material. So it's some mineral that was brought in from a distance and then deposited. So syntaxial, basically same. Antitaxial, different. Now, this drawing from the book is a little confusing. Antitaxial on the left, syntaxial on the right. So on the right it means it's the same material. The reason I say it's a little confusing is because the shape of the grains is visible on both the left and the right. What you want to focus on is the fact that in these right ones, where it's syntaxial, same material, the area in here around the crack and getting filled in, same color as the background. So it's just those grains, growing more deposits of the exact same material. Maybe the water eroded, absorbed and dissolved some nearby and then came and deposited in this joint, but it's depositing like material as the surrounding rock on either side of the joint. In this antitaxial, you notice the area inside is darker. It's a little bit different color. That's supposed to indicate different mineral. So maybe these are quartz and feldspar grains, and in the syntaxial it's depositing quartz and feldspar in the joint. In this antitaxial, again, quartz and feldspar grains, but maybe it's depositing halite, or maybe it's depositing calcite. It's some different mineral. And you can see here that you can have multiple stages. You can have crack, fills in, then new cracks, and fills in, and new cracks, and fills in. It doesn't have to be all one set growth. The way it fills in can tell you something about the stresses, the stress direction, and the order of events. For example, when the stresses are perpendicular to the crack, you get veins that are perpendicular to the crack. So the joint is left-right, the tension stress is up-down, and the veins are up-down, or the fibrous fill of the vein is up-down. On the other hand, on the right-hand side here, we have a joint, a crack going left-right, but our tension stress is angled kind of a northeast-southwest, or a top right, bottom left. So our veins are fibrous in the top right, bottom left orientation. Now case A has tension in line with the fibrous growth perpendicular to our joint. Then later, two cracks form at the contact between our fibrous vein and the surrounding rock. That is a weak point. So it's logical that a crack could form right there. Basically, it decouples from the vein fill, and the secondary stress was at an angle, and therefore the new vein fill that's still fibrous is at an angle. So we have older orthogonal veins in the center of younger angled veins, or angled fibers. On the other hand, case B started out an orthogonal alignment where you had tension up-down and your joint crack was left-right, fibrous vein, and then a crack formed down the center of that fibrous vein. A weaker material. It's the other logical way that you can get a new crack there. It's highly unlikely that you'll get a crack in the main rock within close proximity because stress shadows, and the vein is a much weaker material. So in this case, we started out with the orthogonal stress, and then we got an oblique stress, just oblique meaning at an angle, crack down the center, and so then we have the top right, bottom left orientation of our stress, and so a top right, bottom left orientation of the new fibrous vein fill in the center of the older orthogonal. And so you can see these different kind of patterns, and sometimes in an actual vein you can see that without any microscope or anything like that, depending on the type of mineral. In both cases, the order of stresses were identical. In both cases, we started with the up-down stress and then changed to the angled stress. But we ended up with two different vein patterns. They're telling us the same thing. And it makes sense because the joint is going to form when we have a perpendicular tension stress, just cracking it open with no movement. If there was movement, it wouldn't be a joint, it would be a fault. Later, we can get either another orthogonal tension, or we can get this oblique tension. So lineaments. Finishing up the chapter with lineaments. This is a term you hear a lot in geology. So what is it? Well, fortunately it's a really simple thing. A lineament is simply a linear feature that you can see on the ground. From aerial photos, satellites, topographic maps, it's a big line-like feature that shows up on a large scale. Here you can see this aerial photograph, and we've got a few different linear features. We have the really big obvious one going from top left to bottom right, and then we have some linear features coming off of it. So we've got the one big fault, and then we have some joints coming off of that fault, just like we saw in that little cartoon drawing quite a few slides ago, we've got some tension joints along the edge of a transform fault. Here's a satellite image, so much higher up. Again, you can see some linear features. There's this big kind of top left to bottom right linear feature, and then there's another linear feature coming off of it. A lot of times rivers end up in these lineaments because if there's a low feature because of cracking, the fault or joint, water will start flowing into the low area and then flowing downhill and eroding, and you get a river in a joint or even within a fault. Thing with a fault though is it can go through multiple layers, and so a river won't necessarily stay, it can lose water, whereas a joint is going to stop when it reaches the layer below. Therefore, it's a great place for rivers to form. Rivers very frequently follow joints. Even orthogonal ones. You can have an orthogonal joint system, and then you can have a river that's flowing and it's got some right angles in it because it's following the joint pattern. It's really cool looking, actually. Well, I think. So, anyways, that finishes it up. Lineaments are just large-scale linear features you can see from the sky, caused by joints and faults.